A computer's processor, it's this little universe of pure logic, right? It's firing away at speeds we can barely even imagine. But what good is all that speed if it can't talk to the outside world? You know, the keyboards, the screens, the hard drives, us. So how does it manage to talk to our slow physical world without grinding to a complete halt? Well, that's exactly what we're going to unpack today.
Hey, and a huge welcome back to everyone who's been following our operating systems playlist. We've already gone through the guts of process and memory management. Today, we're tackling the next giant piece of the puzzle, how the OS actually talks to the hardware. We're diving into the world of input-output, or I/O.
So let me just ask you this. Have you ever stopped to think about why your computer, with its processor doing billions of things a second, doesn't just lock up completely while you're saving a giant video file? I mean, it feels like it should, right? But it doesn't. And the reason it doesn't is, honestly, a masterpiece of OS design.
And it all comes down to this one fundamental problem, which I like to call the great speed dilemma. This is the core challenge the operating system is solving for you, literally every single second. Just look at the insane difference here. Your CPU operates in nanoseconds. That's billions of a second. A classic mechanical hard drive is working in milliseconds, thousandths of a second. We're talking about the CPU being thousands, sometimes millions of times faster than the thing it needs to get data from. If the CPU just had to sit there and wait, well, it would be the most inefficient system you could possibly imagine. Total waste of power.
And this is where the OS steps in. It's the hero of the story. It acts as this brilliant, unbelievably quick traffic controller. Its whole job is to manage this completely mismatched relationship between the lightning-fast CPU and the slow-moving outside world, and make it all work so smoothly that you never even notice the difference.
So, to manage all this traffic, the OS first needs to know what it's dealing with. It starts by sorting all the hardware it talks to into two big categories: block devices and character devices.
So on one side, you've got block devices. These are your hard drives, your SSDs. Think of them like a library with numbered shelves. They move data in these fixed-sized chunks called blocks, and every single block has a specific address, so you can just jump directly to the data you need. Then on the other side, you've got character devices. This is more like a river of data. Think about your keyboard or your mouse. It's just a stream of characters or coordinates, one after another. There are no addresses, it's just a constant flow.
Now, here's a really key point. The OS doesn't talk directly to, say, the spinning metal platters in a hard drive. That would be absolute chaos. Instead, it talks to a middleman, this specialized little chip called a device controller. You can think of it as the hardware's personal translator. It takes the general commands from the OS and turns them into the very specific electrical signals that the actual device can understand.
Okay, so the OS knows what kind of device it's talking to, and it knows it has to go through this controller. But how does that conversation actually happen? Well, it's got a few very clever strategies up its sleeve.
First, there's the kinda dumb old way, programmed I/O. This is basically the CPU acting like a kid in the back of a car, constantly asking, "Are we there yet? Are we there yet?" It just wastes all its time checking on the device. Then there's the much, much smarter way, interrupts. This is like a doorbell. The CPU tells the device what to do, goes off and does other useful stuff, and then the device rings the bell when it's done. And for the really big data transfers, there's direct memory access, or DMA, which is basically delegating the whole job to someone else.
And I really can't overstate this. Interrupts are the game-changing innovation that made modern multitasking possible. By letting the device signal the CPU when it needs attention, the CPU is totally free. It can go run other programs, update your UI, whatever, all in those tiny little gaps of time while it's waiting for a file to download. It's genius. So this is how that whole elegant dance works. The device, let's say your network card, gets some data, it sends a signal, the CPU immediately stops what it's doing, puts a bookmark in its work, we call this saving its state, and jumps to a special bit of code called an interrupt handler to deal with the new data. Once it's done, it picks its bookmark back up, restores its state, and carries on like nothing ever happened. It's incredible.
But what about those huge file transfers, right? Using an interrupt for every single tiny piece of a gigabyte file would totally overwhelm the CPU. That's where DMA is a lifesaver. The OS basically tells a special DMA controller, look, you go handle this. Copy this huge chunk of data from the hard drive directly over to memory. Don't bug me about it, just send me one interrupt when the entire thing is finished. The CPU, our busy manager, is now totally free to do more important work.
Okay, we've got one final, absolutely critical piece of this entire software puzzle. I mean, think about it. You've got all these different devices from different companies, all speaking slightly different languages. How on earth does the OS know how to talk to every single one of them? The answer is the device driver. You've heard of drivers before, right? This is what they actually do. A driver is basically a custom-written instruction manual for one specific piece of hardware, usually written by the people who made it. It's the software that translates the OS's generic commands like read into the very specific commands that one particular device controller understands. So, the driver handles the whole shebang for its device. It wakes it up, gets transfers ready, it handles those interrupts we were just talking about, and it cleans up any errors. And the coolest part is that they can be loaded on the fly. That's exactly what's happening when you plug in a new mouse. Your OS finds the right driver, loads it up, and boom, it just starts working.
So let's just take a step back for a second. We've talked about controllers, interrupts, DMA, drivers. It sounds complicated, but when you look at how it all fits together, the whole system is an absolute stroke of genius.
Because the goal of all of this, the big idea, is something called abstraction. The operating system takes this chaotic world of thousands of different messy, incompatible hardware devices, and it hides all that messiness. It presents all of them to your applications through one single, clean, simple interface. The programmer making a video game doesn't need to know if you're using an NVIDIA card or an AMD card. They just tell the OS, draw this on the screen, and the OS uses the right driver to handle the rest.
So here's the thought I want to leave you with. The next time you plug a new webcam or a USB stick into your computer and it just works, remember what's happening. It is not magic. It's your operating system in a split second finding and loading a new instruction manual, the driver, and starting up a brand new, perfectly managed conversation with a piece of the outside world, all without you even noticing.
And that, in a nutshell, is the beautiful system your computer uses to talk to everything around it. If this helped connect some dots for you, do me a huge favor and smash that like button. It really does help us out. And of course, make sure you're subscribed so you don't miss the next deep dive in our operating system series. Thanks for watching.